Okay, welcome back. Last time we were looking at like a pendulum with a spring kind of support. So as it's swinging, it's also stretching. And the main thing that we were trying to get to was equations of motion. We can keep forging ahead and just keep doing equations of motion, but I did want to stop here and figure out like, what is an equation of motion? Like, what do you think this is telling us? When we have, when I say like these are, so it's coming up, when I say these two equations of motion are the equations I need for a pendulum, what does that tell us? Does it tell us anything, or is this just like nonsense math for the sake of like doing math? What is this? Why go through all this work to get to these two equations? Yeah.
At least for the second one, it tells us the angular acceleration.
Angular acceleration. That, what does it tell us about angular acceleration? Is it constant?
It's not constant, it changes
With angle, yeah. So the bigger the angle, the more acceleration we have, right? And then here we also have that r term, and we made the assumption that r is for the most part changing just a little bit. So we could probably drop in like an g over L0 for that, at least as a first approximation. Yeah, that makes sense. What about this first one? Have you seen an equation like this before? What's that k over m? Have we seen that before, or have you seen it? No? Yeah, spring constant over mass. Yep. So that one, last time this came up was back in homework 1. Where we came up with like a is negative k over mx. And those are like natural frequencies of the spring and the mass for that, like for just the up-down motion, like just the radial. So these equations of motion, they tell you a lot about like, what is this thing gonna do without knowing specifics about like, where did it start, or like what's its current speed. You still get things like what's the natural frequency, and in this case 2 equations of motion have 2 natural frequencies, both that g over r and k over m. Those are both omega squared, like 1 and 2. And the more moving parts you have, the more degrees of freedom, the more natural frequencies or kind of time constants you're going to end up with. Depends on if it's stable or unstable. Stable stuff vibrates, unstable stuff like just disappear, like takes off to infinity. So you get a lot of information just from these differential equations. Is there? I'm just hanging out, just raising the roof. Anyway, that's why we're doing this. Get to those differential equations, and then from there we can like move on and try to get natural frequency. If we want to know what's going to happen. We can integrate these and find like this is theta as a function of time. And we'll do that in the project. This module, the main thing, and also like this class, nothing else, if nothing else, free body diagrams, equations of motion. It's like the two things that you should get out of this class. Everything else is sort of like extra math and pulling this from there, but the core engineering principle is like, can you draw forces on a body, show what's causing motion, and then write out, this is the differential equation of that motion. It's like the two core important principles. That's what I think. Other people might think it's like, I don't know, calculus. Calculus is the most important thing you'll ever learn. Yeah, I don't know. You gotta use it for something, right? Okay, so the next problem that we have is, or are there other questions? Sorry, I ask questions, but you probably still have questions, being that you're new to this subject and here to learn from a brilliant mind such as myself. Like, we finally have the person that we need to teach us these difficult concepts. I think that's like the model of the university. It's like, just put a genius in the room with other people and they'll learn through osmosis somehow. But it's a lot more complicated than that. It's like a whole learning journey. You have to like recognize that there is something missing in yourself and then go after it, like work towards something new. But no work today. No learning work. All right, let's move on then. All right, we have a mass. Wait, end of a rope. What? This is not the right problem. We want the lunar rover. I grabbed the wrong one. 330. Copy. Try this again. All right, lunar rover, 200 kilograms. It's gonna move constant speed up and over a hill. The hill has radius 100 meters, and the acceleration, because we're on the moon, it's what is that? 1/5? A fifth of, yeah. Like normally gravity's like 10, here it's 2, so about 1/5. How fast can the rover travel over this hill without like getting some air, you know, like Fast and Furious style? What do you think? Where do you start here? Free body diagram? Okay. Yeah, we could do that. All right. What do you think? What does it look like? Then I'm gonna write out kinetic, since it is moving, I wanna know kinetic diagram. Like, what does that look like too? So we can take a second, try drawing that one out. Oh, sorry, I missed all the chat because my window is like a green screen right now. So let's see, what do we got? Oh no, we haven't done any Lagrangian or Hamiltonian stuff.
Yeah, I was pretty concerned about that because I was like, you should have like 25 of those. Disappeared. You're gonna have to search that ugly box and you see people like that. Like at least 10. I have 3. You got 3. Well, maybe I can check the flyer. If you have a bunch of 20 Ks, you can, but I know you can't do that with 1 Ks. You need like 71 Ks. You know? People take them and then they share it with others, so like your part goes to somebody three people down, and they either lose it or they forget it in their building. Someone probably picked it up. If you lay your stuff out everywhere, someone probably took your bag. I bought a little clear cubicle box from Harbor Freight to home, and I was using it because I was like, I can't have this happen.
And you know how I am, I lay everything out, so
You should get a box. You should get a box.
it's already the second project. I have a box. Yes, all of us are trying to because it's like $3.
Wires?
I'm gonna try to ask somebody to like let me borrow this.
I know there's an electrician shop in Walker that you should be able to travel as fast. No. We call it. I'll be here. I won't be here too late because last night I slept through my first class. No, I was don't worry about that. I slept through my alarm clock. That's a first. My alarm clock's like an end all be all. It seems it was not the end all be all. Well, there's still floors. Or change it. That's the where's the photos? So yeah, so the force would be just like yeah. What's the matter? Well, like catch up. You do not understand. Do your exam stuff today. Just watch 3,000. Never was no acceleration. I mean, they're around like 1.5 and it's if you go almost all the way up and then right all the way to the right. There's a little like hidden compartment. You have to fall into the mountains. It's like there's like a crumbling wall that you jump and break. And once it's time you go in, you go down, you go left, you go down, you go right, bam, catch. And I was like, oh my god, there is a little bit.
It's like in the bench.
No, it's on the opposite side. Bench is on the left. This one's on like the far top right, underneath the purified ducts.
I mean, I don't need it at home,
But oh, I found out where the explosive area was there. Yeah, we were like, use the local thing. So I don't know why we kept missing it. I did it a singular time, like direct. So I went all the way up here, then I activated it down here. You blew a hole up through here. So I put one up here and it blew through down there. So we were just missing. We were just missing. But yeah, so all the way up here is like you poke one of those big monsters that fall on you. And if you go right, this is a blocked out area. So you gotta go up and around. You have to fall. This is for all those things that jump back in the fire. You gotta fall into the sludge. Go up, down, and around. And remember, you know the area where it's like how far away.
All right, so I saw this part I liked. Some people, before they drew the free body diagram, they thought, all right, let me figure out what this rover looks like. As we're going up and over the hill. So we have like a rover, it's going up and over a hill, we're approximating constant curvature, and now I can say, all right, well, it doesn't matter where I am on the hill, NG is still pointing down. Some nice insights is that along, so if this is kind of like current spot of the hill, right? Along the hill, like the only thing overcoming gravity to maintain constant speed, it's got to be like the motor pushing us, but that torque is not directly pushing us forward. Torque turns into friction. Friction pushes us up and over. So there's some kind of friction. It's big enough to make sure V doesn't change, at least like that velocity. At least this is, I'm like interpreting the graphs, like the things that I saw. Okay. What else did we have? Which one? Normal force, yeah. So normal to wherever that curve is, wherever you are on the curve, something that way. And then the kinetic diagrams, I saw a lot of blank dots and some discussion of like, if if speed is constant, no acceleration.
But I guess that's wrong based on, so I guess because you go up, you were over a thrust from the hill, you're tiny top, like you're looking at your
Yeah, so at every point, we keep having to change where our speed is going. So if we say that there is no acceleration, then these forces they have to balance out. Like friction is whatever, normal force is whatever. They would have to all equal 0. And we could drive as fast as we want. We could do speed of sound up and over this hill, and we'll stay in contact the entire time. But that's not, like, intuitively you know that's not true. Like, if you go over a speed bump, sooner or later you're gonna get some air as you go over that speed bump. So there's something missing. So we could look at it the same way of like, we have the curve. Is there any acceleration along the curve? I'll call it like a tangent. Is there a tangent acceleration? Maybe? What is that? What would the tangent acceleration be? Centripetal should be like towards the center, right? Yeah, so this one's not 90 degrees to that centripetal acceleration. So what is this tangent acceleration describing? Yeah, so at that moment, like what's happening in that direction of motion. So this is this is a new frame of, like a new coordinate frame, at least new to our discussions here in class. Like, it's in the textbook. It is a widely used frame of reference. It's called intrinsic coordinates, where you're just talking about what's happening to the actual thing moving. So our frame of reference is position is always 0. Like, there is no position, because it's the frame of reference starts at the person driving and it goes from there. So we can have a velocity, we can have acceleration, but there is no, positions are always relative to the thing moving. Kind of a weird thing to do, but the nice part is that this tangent acceleration is a change in speed along that curve. So we can say tangent acceleration is dv dt, which means there's no acceleration. Yeah. So along the curve, so as we're going up and over, we're moving at a constant speed, so our dv dt is 0. So that tangent acceleration is 0 as we're moving along. And it's only describing speed. Yeah.
How can we drive on the if its value is 0?
Oh, we can just say equals 0. Like because like the component is still there. It's just that component is equal to 0. And it's gotta be tangent to the curve is the main thing. At least this is one way to do it. Another way would be like, hey, we're moving around something circular. Let me put it in cylindrical coordinates, look at what the change in angle is and all of that. What about this, like, normal acceleration? What is that one? Yeah. That one's centripetal acceleration. This is the case where physics teachers say there's no such thing as centrifugal force, because it belongs in your kinetic diagram. I can't put a centripetal acceleration here and a centrifugal force here. Choose one. It's one or the other. So if I wanted, I could delete this and say it's over here. Kind of a weird way to do it, but technically it is a force, because mass times acceleration is a Newton. But I like to leave it in my kinetic diagram because it's describing motion rather than like a force due to motion. And centripetal acceleration, do you remember what that one is? No. This one, it's not like we've been talking about it a lot, but it's somewhere buried in the archives of the brain. Yeah.
Is it omega r squared?
Omega r squared. Yeah, we could say that it's like r theta dot squared. Is that what you're thinking of? Yeah. That one, that is centripetal acceleration. But if we want to talk about it in terms of like speed around a curve, it's also mv squared over r. And they're both exact, it's the same thing, whether you find like theta dot and r, or you find v squared in r. It's the same, you're describing the same like motion, same acceleration. Sorry, I covered it up with my vanity bubble. It's coming up in a second. There, here we go. All right, so now we have forces. We have a kinetic diagram. how fast can we go? Because that's the real question. It's like pedal to the metal, how fast do we need to go over this hill? Really, the cool question is how fast, what's the minimum speed to get some sweet air? The lame question is like, how slow do we need to go before we lose contact? So let's figure out minimum speed before we like, ta-da, like nail it, light the fireworks. Trying to maximum speed. What's our minimum speed for fireworks? Where do you go from here? Do you know where to go from here? Any ideas? Toss that. Brainstorming. No bad ideas. Brainstorming. Just like, where do we go? Yeah.
Could you set it equal to normal force? Because if normal force is equal to 0, then you have longer question.
Yeah. So if our normal force is 0, then we're not touching the ground anymore. So that's a great. So here, N is, if it's more than or equal to 0, that means it's on ground. If N is less than 0, then we get some air. Yeah? Yeah, I mean, it can be. Physically, no, since tires can't create negative normal force. But if you were trying to design a car that could have negative N forces, maybe it would have like magnets and it's driving on a steel track or like a train track that you like clamp onto. Sorry.
Why is if normal force equal to 0 still mean that it's on ground?
If it's equal to 0, then that's kind of like right at the cutoff point where you haven't left the ground, but you're also not creating any contact with the ground. So your suspension is completely like unloaded in this case, but you haven't, like, your wheels haven't left the ground. But if you get to a point where it's where you're calculating like N is less than, like it's an actual negative number, at that point you would have left, like somehow you have enough momentum that you would have just taken off. That's why I said like more than equal to rather than like more than.
So if you just set the N force, the normal force equal to NV squared over R, because that's the centrifugal force that's keeping it on the ground.
So you think N equals mv squared over R?
Or
So V is 0?
no. Well, we would find, then we would convert the normal force into the component force for MP, right?
Okay, so then, yeah, exactly. So when we're looking at these,
So we call it like.
we have two components of mg, right? Like one of them is keeping us on the hill, the other one's kind of pulling us back down the hill. Yeah. Okay.
So we could just set that equal to the one that's keeping us on the hill to make to see how fast the velocity is, because we already have the mass, the radius.
Yeah. Okay. I like that. Yeah, give it a shot. So we'll take the components of mg that are normal and then set that equal, and then we have the normal force, we have that component of mg, set that equal to v squared over r, and we'll see where we end up. Yeah, where like they have to be somehow connected to each other.
So it would just be like cosine, yeah, cosine.
Cosine? Okay. Yeah, yeah.
because you passed 90? Or are you just
Over 90?
Yeah.
Because the centrifugal force is based on the velocity. You can set it equal to the inside force that's sitting on the inside. It was equal to. Yeah.
You want to exceed the velocity.
It flies away. The only issue is that's a single question. But the component force we have to use.
Okay, yeah, that is a good question. Like, does it depend on where you are on it? For the whole thing, okay, yeah.
You can memorize 3, 4, 5 strategies or
So, you see like the vectors, oh, for choose normal?
It's tangent.
Okay.
Then does that make sense?
Yeah, like normal.
Yeah.
Normal force is a normal.
Yeah,
Yeah.
Oh, so to go perpendicular to tangent.
Yeah, a normal angle
From a tangent.
tangent is parallel.
Yeah.
Normal.
But normal will always be perpendicular from a tangent.
Yes.
Okay.
Yeah. Yeah, it should.
That's
And the
and anytime this is tangent line.
Yeah,
Maybe a
it's
normal
normal.
line.
Normal.
I see. Okay. I'm not sure I understand setting the like the lines of graphs to the centrifugal acceleration.
Yeah.
Because bubbles are moving barrels, so you're pushing it, it's into that. So how to read this find the velocity to centrifugal acceleration help us find the velocity at which it moves.
How does
It's like finding if the horizontal velocity, the cosine of the graph is 0, is that equal to the centrifugal acceleration, which is finding how much it accelerates back into the hill.
So, 90 degrees.
That's whatever speed.
Yeah.
So then how would that,
Which means that
that speed
the
would have to
velocity
be
has to be 0 because
Did you forget to account for gravity?
So are you saying
I did.
NV squared R equals mg?
Yeah, now something is wrong. Why isn't gravity working? Unless they
So
forgot to turn on the
there's kind of like
gravity.
two forces.
Well, you have an accounting
I haven't accounted for it. Mass is
Discount
discounted
NV
because
because
it's
it's
just
just
other way.
Maybe science though.
It might be so.
If you said,
But let's do
equals
that.
0,
Okay, yep.
but number force equals 0,
No.
Yeah, so now we just have one equation.
If we use the cosine, so that this is our force, we use our cosine multiplied by the force, so that gives us.
Yeah, but that would give us one.
I guess if you use this one, then it would be this force times the force of gravity, so you would
Oh,
get
wait,
this
this
force
is,
times
yeah, intuition. This is saying that it's less than that.
opposite over adjacent times
Yeah, that's what it was.
adjacent, which would be mg.
That would be 10.
That would be, no, that's not.
It'd be,
So this is
cotangent,
Cosine
cotangent.
of gravity is equal to
Because tangent of theta, tan of theta, right, equals opposite over adjacent. Adjacent equals mg, right? If you multiply mg by 10 and multiply it by opposite, which is your horizontal force. So if you multiply it by cotangent,
No, but MG is the hypotenuse versus the
oh, that's your hypotenuse. They don't use tangent.
It has to be hypotenuse because it's the biggest value.
I like triangles relative to the ground.
Not relative to magnitude.
Exactly. I don't like this where the square triangle is sitting pretty at an angle.
Maybe I got the equation wrong somehow. Is it mg cosine of theta?
You just tried it because I guess if I were to draw.
All right, so let's give it a shot. Here's what I've seen so far. What do we think? Oh, it's coming up. It's slow. Oh God. Why is it so slow?
Okay. Oh, it's minus.
What do we think? How does that look? What?
That makes sense.
And then set n to 0? Or, yeah, what do you think? Why is n equal to mg cosine theta? If we were not accelerating, then that's true. So on a constant slope, definitely, n is mg cosine theta. But here the slope is changing, so we're changing direction. So we've got both that acceleration and n and mg cosine. But yeah, you're right. Like you've seen that, and kind of like taking some experience there. Like most of the time, these two terms are equal to 0 because it's usually kind of rolling up or down a ramp, and so n is mg cosine. But in this case, it's not. It's not equal to. The two of them are kind of combating each other to say like, leave the ramp. No, stay on the ramp. Yeah. Cool. All right, so here, this is my suggestion. You can go from here whatever you want to do, but here's a suggested method that I like to do. Solve for n. So it's mv squared. Oh wait, sorry. It is mg cosine theta minus mv squared over r. I want n to be more than or equal to 0. So therefore, the thing that I just said n is equal to, that has to be more than equal to 0. This is my own like preferred approach, so I can keep track of, should v be smaller, should it be more than, like what am I solving? When I say n is 0, what happens to the rest of my variables? And that's the way that I like to go about it. If you like a different way, or you have like some other intuition into it, there's more than one way to do it, but that's where I would go to start. All right, plug and chug. What's our answer? How fast can we go?
Trying to catch up on this part.
Yeah.
This part makes sense. I think I was screwing up because with our free body diagram, I still don't know this in 2.5 years of doing this. The mg value having this being the hypotenuse and this being the right angle always throws me off. My brain always doesn't have this. And so like I would think this is mg, and then if I were to use theta here, cosine would be this over that, but multiplying that by that would give you earlier, co-tangible wood. Because it would, mathematically.
Okay.
It'd be uglier though, much uglier to solve.
So the thing that I like to do, you mind if I draw? Like, this is my angle, this is NG. So think of like NG cosine theta. And we're back here again, except that instead of the equal sign, it's equal or less.
Do you have your minus n?
But we got rid of the minus and by setting it equal to 0. Well, greater than, greater than.
Okay.
Yeah. Like, so if I think about F1 is NG cosine theta, the theta is 0, then F1 is NG. So it's gotta be, that's gotta be this component. Pointing out, because if I'm at 0, then it's straight down. Yeah. So that's what I like to do. It's like
Like a math group. A
Yeah.
sandwich check.
yeah, like,
Okay.
yeah, just like, okay, if I set this equal to 0, will these parallel, or do I get to 0, or do I get to max?
Okay.
I guess
This is referential.
I guess
I'll
this
work
makes
around
sense.
it.
I guess this makes sense because it's like I got this equation.
Okay.
Velocity is less than equal to the radius times gravity times cosine of theta.
Okay.
So that means that the value you need for velocity changes.
Oh, okay. So as we're moving, it's different.
Yeah, I think so.
So V is more than or less than?
V is less than or equal to r square root of r times g times cosine of theta. The only issue is if it's 90 degrees, it means that V has to be equal to or less than 0. Because cosine of 90 is 0.
So if we're 90 degrees off, we have to be moving at 0.
Oh, you only have, yeah, you don't even have to be moving.
I mean, that makes sense. If you're moving at a 0 degree parallel to the floor, you're going to be moving at max. If you point your car straight upwards, all the wheels are off the ground, you don't move anywhere.
What is our angle theta? Where is it measuring relative to?
Relative to the floor, I think. Relative to the floor, you know?
Yeah.
Oh, it's the whole relative to the gravity. Yeah.
Okay.
If you're at the apex, go to 0.
So that means that there is no normal
Okay.
force.
So
And 90.
so I said mg cosine theta. I could have said mg sine theta. What angle am I even talking about? Yeah. And the normal, so down versus normal. Like this is theta. I think it'll catch up. Is that one? Is that what you mean? Is that, what do people think about that? Is that the theta that we all had in our heads? Different theta?
The other one, I just had the triangle facing it.
Is this it?
So this is also describing like the current slope that we're at,
Okay.
right?
Oh, that makes sense. So that
Yeah.
90 degrees will be like flat and will be falling down.
Yeah, so we did some algebra. We got to V is less than square root RG cosine theta. And okay, at pi over 2, we have cosine theta is 0. Realistically, on a hill, what's the maximum incline that you've ever experienced on any hill that you've ever been on? 45? You think 45? What do you think?
Probably like
20, maybe 20 degrees? 25? Okay. Have you seen like percent grades on a road.
Those are confusing.
What's a 20% grade?
I think every 100 feet forward, you go 20% down.
Okay.
I think I'm messing it up. I know it's
Something.
for trucks.
Yeah, yeah.
I know 45 degrees is grade 1.
Grade 1, 100,
Like
right?
grade, so it's
Yeah,
like, what would that be? Like 27 and a half is officially.
yeah, yeah. Okay. So the only time I've ever been on a 45-degree incline was climbing up the backside of Half Dome, and it was for all of like 5 feet. That was actually 45-degree angles. It felt like I was climbing this wall. Like it's so mind-numbingly steep that it gives you like vertigo. So 45 degrees is crazy steep. It's like steeper than almost as steep as like climbing gyms can get. Sometimes they have like whatever backwards angles or whatever, but so 45 degrees, very, very steep. Probably the steepest, like even on a slope, if you're trying to like get a lot of speed, probably about 20 degrees, like maybe 20-ish. But here we're talking about a hill, so like Horse Barn Hill. Does Horse Barn Hill get to 20 degrees? Probably not. Because really, like if we think of the hill as like some kind of constant R is 100 meters, it doesn't start down there. It starts like way up here. So we only have an angle, yeah, like maybe 20, maybe it goes 20 to 0, then back to 20 or something like that. Is it okay to call it a small angle then? Small angle? What's a small angle for cosine theta? What would that be? A 1? Yeah, so we could just say this whole thing, square root RG, call it a day, right? Oh, and we're right on time. It's 10 after, well, it's 8 after, but take those 2 minutes, we'll pocket them, and we'll come back next time on Friday. Sound like a plan?
It's 2 feet.
All right, thanks a lot.